Good afternoon. Thanks so much for coming to our first distinguished lecture in the Paul G. Allen School of Computer Science and Engineering for 2023. It's my pleasure to introduce Amin Vahdat, our speaker. Amin is currently fellow and vice president of Google, where he's responsible for essentially everything that goes in the data center. That includes computation, storage, networks, operating systems, machine learning accelerators, everything that runs Google's workloads. Amin received his PhD from UC Berkeley in 1998. He spent 15 years as a professor in academia, first at Duke, then at UCSD, where he was SAIC professor and director of the Center for Network Systems. In 2012, he joined Google. He's won a huge number of Best Paper Awards and Test of Time Awards, from major systems conferences. He's the recipient of a Sloan Fellowship, fellow of the ACM, and in 2020, Amin received the SIGCOMM Lifetime Achievement Award for groundbreaking contributions to data center and wide area networks. Finally, I want to note that Amin spent 2 years in UWCSE while finishing his thesis, something many of us remember. So I'd like to welcome Amin back home to give this talk.
Thank you very much, Hank, for the kind introduction. It's a real honor and privilege for me to be here. Been really looking forward to this. Hank didn't mention that, so my PhD advisor is Tom Anderson. It's a real privilege to have Tom in the audience, which makes Hank and Ed my grand advisors. My time at UW actually changed my life. And I mean that not with hyperbole, but with full sincerity. I learned a tremendous amount technically, but I think actually the thing I want to highlight and really relay to you all is you all are in a special place culturally. I think that sort of the welcome I got at the University of Washington was unexpected, to say the least, for me, and something that in my own way I've been trying to pay forward ever since. So thank you, and it's something I've been looking forward to having the chance to give this presentation here. A couple of housekeeping notes on this presentation. The vast majority of the work I'm going to be describing to you here is the work of others. I'll take credit for the errors, but the insights are others. And the other note I'll make is that it's going to have a perspective driven by what my experience is at Google. So a lot of the things you're going to be hearing about are from Google from that perspective, but it's not specific to Google. A lot of it applies to any industry, I think, any other company, lots of great companies out there, academia and more. So today I'll be telling you about what I think is, in my recollection, perhaps the most exciting time in computing over the past 25 years. And sometimes after you've been doing something for a while, you get a little bit jaded. I actually am more excited than ever. So I think that actually right this moment, we are facing a once-in-a-generation inflection point in computing. So a set of design principles and architectures, which I'll be describing for you here, have really fueled the past, depending on how you look at it, 20 or 25 years of computing. And it's been incredible, right? What they've driven and what we've been able to achieve as a result. Lots of people talk about reinvention because reinvention is fun. But I think that actually right this moment, we have the opportunity to reinvent, not because it would be nice to, but because we must. In other words, the design patterns that have fueled the past 20 or 25 years are somewhere between slowing and stopping to stopped. Right? And that means that we're going to have to do things differently. So this really says, given societal demands for computing, we really have a manifest opportunity to write the book on what infrastructure looks like for the next generation. Right? And what I'm going to try to be pointing out here is that a lot of the things that we take for granted today, oh, of course you would do X. Of course you would do it this way. In 2023, were completely non-obvious in 2000. They were radical. You wouldn't imagine building systems that way. In fact, a lot of people might have said in 2000, the way that we're doing things now is the wrong way of doing things. So I think it's actually a really exciting moment where we're going to get to say what seems wrong is going to become how we do things. And I don't exactly know how that's going to play out, but I think the opportunity is just tremendous. OK, so what drives this? I think fundamentally new requirements is the starting point. And I like to refer to this as the 4 S's. Number 1 is societal infrastructure. Increasingly, what we're seeing is that computing is required for our day-to-day functioning. Actually, one of the things that my family reflected on is what would have happened if the pandemic had happened 20 years ago? Just as one simple example, would we have been able to function as a society just 20 years ago? And maybe we would have made do. But, and it was terrible. It has been terrible. I don't want to mitigate it in any way. But we were and are prepared, from whether it's developing vaccines to being able to interact with one another, prepared in fundamentally new ways that just 20 years ago we might not have been. We rely on our computing infrastructure to do a lot. And so this means the reliability has to change dramatically. And the performance and efficiency has to change. So I think that we have delivered, let's say, over the past 20 years, 100x improvements in reliability. We've delivered 1,000x improvements in performance efficiency. These aren't exaggerations. And that's amazing and things we should be proud of. And I would say neither one is enough. Second, security. So our computing infrastructure is constantly under attack, right? Threats internal and external. And what I'll highlight is actually, certainly at Google, internal threats are as big or bigger than external threats. But our infrastructure, and again, not just ours, is constantly under attack. Some of it might be sort of mistakes, but others might be active. We have to be able to survive these kinds of attacks. Third S is sustainable. And what I mean here is, as a starting point, carbon-free computing. We're at a place now where computing, depending on where you look, might consume 1–2% of global power, and maybe might be responsible for 1–2% of global carbon emissions. I'm not an expert on this. We could debate the numbers. But we're also in a place now where the fundamental efficiency of computing per watt is not increasing anymore. If we're going to deliver another 1,000x in capability, we can't deliver 1,000x in watts. So we might be 1 or 2% today, but that better not become 50%, 60%, 90% in the next decade or two. So sustainability is absolutely key. And final S I'll highlight is sovereignty. And essentially, increasingly, and very reasonably, countries are saying, wait a second, am I at the whims of decisions that might be made in another country, let's say the US? Okay? And increasingly, countries and companies are demanding control over the placement of their data and access to their data. This might mean just actually who can access it where it moves, where it's replicated. It might mean, of course, how it's encrypted and how it's transmitted. But the implication here is that, again, 20 years ago, we would have said centralized control is actually not the right way to build large-scale distributed systems. It should be completely decentralized. Today, conventional wisdom says, oh, not decentralized. Of course you're going to do it with centralized control. I see, maybe many of you see, a secular sea change where we're going to have a move back to decentralized because the requirements are changing. And that's going to be very interesting as well. So a look back at the past 20 years. If you do rough math and you say that performance efficiency for constant dollars has improved has doubled every 2 years for the past 20 years, and that's roughly been true, we've delivered a factor of 1,000 capacity, right, to the power 10, simple math, over the past 20 years for the same dollars, right? And that's pretty amazing. And that factor of 1,000 starts to make what was previously thought to be impossible, possible. Right? And over time, it makes what was previously thought to be impossible standard and normal. 20 years ago, the thought of being able to do essentially real-time translation from any language to any other language, or almost any language to any other language, that was the stuff of science fiction. That was what I watched Star Trek, right? And I thought, no, that'll never happen. Now, actually, that what was science fiction is entirely possible, and maybe something that we're going to be delivering in the not-too-distant future. What drove this? Again, these are things that we take as obvious today, entirely non-obvious in the year 2000. We're going to use commodity storage, computes, and network hardware that, because it's commodity, and that it can leverage sort of existing silicon technologies, will double in performance and, more importantly, performance efficiency every 2 years. We're going to leverage cluster-based computing. So this is the notion of scale out. So around the year 2000, the way that you built ever bigger systems and applications was you bought a bigger computer. Right? And it was a very high-end computer, and it was very specialized. So the notion that you'll take commodity parts and you'll scale them out to 100, to 1,000, today to 40,000, 50,000 or more, right? That was thought to be impossible, or at least the wrong way of doing things. And that you would control it centrally, at least logically centrally, was thought to be somewhere between hard and impossible. So, but through these techniques, it allowed reimagining what was possible in scale and capability. And it made it available to developers across the world. So, today, essentially, the internet is the basis for real-time communication across the planet. And again, somewhat surprising, but for us, though we take it for granted, we have real-time access to essentially the totality of human knowledge on our phones via ubiquitous cellular coverage. And this now is something we take for obvious, but and granted, but 20, 25 years ago, we still had encyclopedias. So I could go arbitrarily far back. I'll go back to this interesting article from the New York Times in 1991, labeled Attack of the Killer Micros. And the idea here is that the companies at the time, let's say the Crays of the world, digital equipment corporations of the world, et cetera, who were building these scale-up computers, were starting to be worried about clusters of commodity, let's say personal computers or workstations. And the notion that you could hook them up to one another via a commodity network and start to beat these scale-up computers on performance. So the seeds of the next revolution were being laid. I mean, there was a New York Times article maybe 10 years before these kinds of things becoming somewhat commonplace that said, hey, this is happening. The companies are starting to get worried about it. It took probably another decade or so where actually, okay, so any internet company that was going to do large-scale computing and storage would be doing it based on clusters. And these clusters continue to grow in scale. So this is a picture of one of our data centers in Council Bluffs, Iowa, and massive scale, massive replication, but also a lot of homogeneity here. And that's also important, which makes it easier to build out and to operate. So with this fixed infrastructure, one of these buildings might be 30 megawatts, a lot of power. You might put 60,000 servers in there, 120,000 disks. Network with all-to-all uniform capacity, right? Full flat bandwidth. What that meant is that you didn't care where your jobs ran. You had full, today that might mean 100 gigabits per second of bandwidth between any two servers in the same building. Tomorrow it'll mean 200 gigabits per second. But the point here is that you could have the same experience irrespective of where you ran. We also leveraged loose coupling and fault tolerance. The idea here was that you had to build your services such that if you're running on 1,000 servers, or whatever the number was, you built it such that at any point in time, some fraction of your servers were going to fail. Right? And this was a complexity that you took on to leverage the scale-out capability. So looking at it from the perspective of Google, this led to a reimagining of how we built all kinds of different systems. So I have names of pieces of infrastructure here. Let me map these to different ideas and different, what I would say, breakthroughs in terms of how we built computing. So it started with a system called GFS. And the idea with GFS is that you could actually leverage all the disks in a cluster as a single unified file system with centralized control. 2002, at the time, actually, and I'll relay a short story, I was on the program committee. This paper was submitted to SOSP 2003, and we almost rejected this paper. Crazy talk of centralized control, 10,000 disks. That's not how you build file systems. Couldn't be a good idea. Unfortunately, we got lucky. Fortunately, we accepted the paper. I think many of us would have been kicking ourselves if we hadn't. But the point was, the conventional wisdom said decentralized. Conventional wisdom at the time said peer-to-peer. So this was one applied to a system like MapReduce for scale out with analytics. Systems like Bigtable that said, hey, you know what? I can treat all the disks in my data center as one big relational table that I can read and write. I can now treat my cluster as one scheduling domain and be able to start jobs, stop jobs, move jobs through a system like Borg. More storage systems, systems like Spanner that showed how you would replicate content across the wide area synchronously. And of course, machine learning, which I'll be talking about more later. But the point was that this basis for cluster-based computing really said, we are going to reimagine how we do computing. And actually, each one of these little highlighted systems here reflected deep, deep debates and very negative reactions on the part of many in the community. Right, so none of these were obvious things. That's what I want to point out. Maybe in 2023, we would say, yeah, of course, this is how you would do it. It's conventional wisdom today. Back then, each of these were major sources of debate, right, between communities in terms of how you would proceed. OK, so we've gotten here. Why not just keep going? Right? So that's the key question. These graphs, a little bit, they look like a little bit like cartoons, but they're actual data from at least Google that shows what's been happening to CPU performance trends, the cost of DRAM per byte, the cost of storage per byte, and power efficiency of our infrastructure over time. So the x-axis is time, and the y-axis is normalized to some units. Essentially, the power of how we built computing over the last generation was driven by the fact that previously you got a doubling in performance every couple of years, or you got half the cost for the same performance every couple of years. We've gone from a place where you could expect, in the end, 40% year-over-year performance improvement for fixed cost, to today, that number is about 3%. Maybe it's 2%, maybe it's 4%, but doubling every couple of years to doubling every 20-something years. And what that says is that if you need the next level, if we are going to deliver another 1000x over the coming 20 years, we can't just wait for the hardware to get cheaper, faster, quote unquote, for free every couple of years. That's over. And in fact, some of the things that the 4S's go after, meaning like security, like sustainability, are counter to the way that we've done things in the past. What I mean by that is, actually, we've introduced a huge number of security vulnerabilities into CPUs, for example, not the subject of this talk, driven by performance, that expose all kinds of side channels. Closing those side channels makes our CPUs slower, or makes them more expensive, or both. So, DRAM, similar kinds of things. Many of the attacks that you may be aware of against DRAM, where you can actually go read someone else's data in DRAM, are driven by the fact that we've pushed hard for those efficiency gains that we now have to give up. So what this says is that actually for fixed, now there's a really interesting bit here. A debate around whether Moore's law is dead or Moore's law isn't dead. It's interesting, I went back and checked. Moore's law says the number of transistors per package doubles every 18 to 24 months. That side of it actually remains, and it's stunning. We're still doubling the number of transistors per package every 18 to 24 months. The problem is that in 2023, we're not doing it for fixed dollars anymore. We're roughly doubling the number of transistors for double the cost. So there's some benefit to that, but and the power also potentially doubles depending on how you're looking at it, and or you're having to go with the equivalent of multi-threading. These technology plateaus say that the previous set of design patterns that we've ridden over the past 20 years actually can't apply anymore, and that's where the necessity bit comes in. So why do we have to reinvent? Massive scale ML training. I'll be talking about that more shortly, but the point there is that I actually, in my time, have not seen anything like this, where the demand for compute is increasing by a factor of 10 every year for now 6 years. We talk about delivering a factor of 1,000 over 20 years, pretty impressive. The demand is up by a factor of 1 million over 6 years. None of our previous design patterns could keep up with that, even as great as they were. So new workloads, new requirements, real-time inference, video, sensors, all exploding. We talked about perhaps the end of Moore's law. I don't think it's the end of Moore's law, but it's the end of the corollaries, which says doubling the number of transistors for fixed power and fixed cost. That side is undeniably over. And then I would say necessity, and this is the key thing, and this is what makes it very exciting for me, and I think for the community. Meeting the demands of computing is easily going to require another 1000x. Like just what we can see right now, actually the demand for storage, the demand for computing is only going up. So what that says is that the conventional wisdom that we've developed and we've gotten reliant upon cannot efficiently scale to meet those needs, and we're going to have to figure out how to do things differently. So the path here and the path forward. I've argued that scale out based on commodity general purpose hardware is essentially now over as a path forward. It's been an amazing journey to this point, right? And we should be proud of it. But to deliver the next 1000x, I'll argue there are 4 top-level things that we're going to have to look at. Number 1 is specialized hardware. And for the first time, actually, specialized hardware makes sense. In the past, when performance efficiency doubled every 2 years, by the time you got your specialized hardware done and you made it programmable, you got beat by general purpose compute. Now, actually, well, if general purpose compute's only got 4%, 3% a year, you actually have more time to deliver the benefits of specialized hardware and the need. I'll argue that the programming model is more important than ever. One of the things that's happened over the past 20 years is we've had to move to multi-threading. I don't think that we actually know how to take advantage of multi-threading to the extent needed today. It's going to get harder moving forward, actually, with the specialized hardware and how we can actually program to it. The last set of design patterns and the massive amount of code that we wrote around loose coupling and fault tolerance are going to have to get revisited, because essentially what we've done over the past 20 years is said the slope of the efficiency curve doesn't matter. What that means is that actually the amount of performance I get out of every server isn't so important as long as I can multiply out to 50,000. Right? Because every 2 years that baseline performance doubles, so let me not work so hard to get lots of performance out of every server as long as I can scale linearly to 50,000 servers in a data center building. I would estimate that we've left a factor of 10 from a speed of light perspective on the table and the efficiency of every one of those servers easily, if not in some cases a factor of 100. In the sort of next epoch, next generation that we're facing, we can't afford to give those factors of 10 and 100 up anymore. So we're going to have to look back at the efficiency of each one of those individual servers while maintaining linear scaling. And then finally, we're going to have to break out of the confines of our individual domains. In other words, we're not going to be able to look at networking or storage or compute or accelerators in isolation. We're going to have to look at systems and really develop metrics that say, what is the efficiency of my systems from the perspective of the user and the application developer. The user might be the person doing machine learning training or video inference or search or something else. But the point is, focusing on the, in the end, easy to optimize benchmarks that focus on a particular domain may not move the needle, and frankly likely won't move the needle on end-to-end system performance, which is what we need to focus on to deliver the next, let's say, 1000x. Okay, so I'm going to be illustrating these 4 design patterns through hopefully 3, but I'm only likely going to get through 2 vignettes, right, that illustrate how these things apply and how they apply end-to-end to deliver some of the benefits that we need. First one is TPU supercomputing, or why judicious specialization matters. So this reflects some custom hardware, tensor processing units that we built at Google for machine learning. And somewhere around 8 years ago, we asked the question, what if all of Google's users were to interact with their devices via voice for 30 seconds every day? And the answer back was we had to do then voice recognition in real time for those users, the inference problem. We did the simple back of the envelope math and realized that we couldn't afford to build infrastructure to support that use case on general purpose computers. And given the improvements in CPUs even back then, 8 years ago, it wasn't just a question of, well, you're being too aggressive, just wait a couple of years or wait 5 years and then it'll be affordable. Fortunately for this particular problem, the computation involved was regular. And so we could imagine building special purpose hardware to support that inference let's say in the end, somewhere around a factor of 100 more efficiently. Right? And you can say that's going to be in terms of power, in terms of space, in terms of cost, or more. This then led to custom systems. You see pictures of them here, supporting training, large-scale training, as well as inference. So what did we do in the end with TPUs? Judicious specialization and application co-design. We built specialized hardware for dense matrix multiplication. Right, so this is not a general purpose compute. This is special hardware for doing matrix multiplication really, really fast. We moved from DRAM connected across a DDR bus, relatively far away from CPUs, to high bandwidth memory that was stacked 3D on top of the TPUs. So we leveraged the fact that we had to feed this dense matrix multiplication really, really fast via high bandwidth memory that sat on top of the TPU. We also added specialized hardware for scatter-gather operations. So we found that actually a lot of the math that went into this was no longer just the regular matrix multiplication, but involved the equivalent of pointer chasing, especially when the matrices wound up being sparse, as some of the next generation use cases wound up being. We didn't leverage Ethernet. And this, and for me, at the time, I was the lead for networking at Google. This was a shocking, horrible decision, right? Ethernet had won every single time for longer than I was alive, or at least as long as I was alive. And now, for the first time, we're saying the answer for connecting these TPUs to one another was not going to be Ethernet. It was going to be a special point-to-point, incredibly high bandwidth. Right? Actually, the point-to-point connectivity from each one of these chips was as fast as the fastest switch chips that you could buy on the market. And it didn't have a layer 2 protocol even. Essentially, it was saying, hey, I know that I'm going to be synchronously dropping parameters across, let's say, 1,024 chips at the time, more now. I'm going to design a network that all it does is drop parameter updates, floating point, integer numbers, whatever, from the registers of one TPU to the registers of another TPU. And this was way lower latency than Ethernet, way lower cost, and we didn't even leverage a CLO topology. Maybe you'll see it later in the talk, but we didn't even leverage a tree. We did a point-to-point torus. All these were conventional wisdom, terrible ideas. But in this particular domain, specialized for this operation, made a ton of sense. We went with liquid cooling, which was, again, counter to all conventional wisdom because all of our data centers at the time were air-cooled. And we went with specialized data representation. Right? We didn't go with the standard IEEE floating point representation or the integer representation. We said we know how to actually come up with a better representation for the data and bake that into the hardware. And I think that if we had made these decisions 5 years earlier, or we're facing a different problem, all of these, like you would look at all of these bullets and say, oh my gosh, who came up with this? Well, the people, this wasn't me, by the way. These were smarter people than me, much wiser people than me. And they made all the right calls. And taken together, this led to somewhere between a factor of 10 to 100, not exaggerating, system efficiency improvement relative to the best that you could do on general purpose CPU in terms of performance, power, cost, virtually any metric that you could think of. I think most importantly, though, is it gave us new capabilities and it allowed us to imagine new things that we could do. So this wasn't just the question of, hey, inference on CPUs was expensive and we made it 30% cheaper. That would have been pretty awesome. It went from, we can't imagine doing this, possibly, to, yeah, actually, we're going to do real-time voice recognition. And we're going to do, in the future, large language models, et cetera, as a result of having this capability. And really breaking conventional wisdom in terms of how you do system design on essentially all imaginable axes. OK, so what are some of the things that we would do with this? I'll give you one example. Palm. This is from now a number of months ago, which is a 540 billion parameter language model that ran for 6 weeks on 6,144 chips, split across 2 TPU pods. This is the version 4 pods. Over the 6 weeks, it carried out 2.56 times 10 to the 24 floating point operations. And I think of note, it ran at 60% hardware efficiency. What this says is that the amount of computation that was done across these 6,000 chips was 60% of the maximum that could have possibly been done, even if you were just doing straight-out matrix multiplication on every chip individually. So pretty impressive for a large-scale distributed run, accounting for failures and everything else, pretty impressive level of efficiency. This is a decoder-only model, so trained on lots of text, for those of you following GPT-3, and many of you probably are, similar to this, with the objective to predict the next word from the preceding set of words. And at the time, it was the largest dense language model trained to date, and in fact, in terms of the parameter size, larger than GPT-3. It brought together a lot of different pieces of Google. I won't go through this in detail, but there were essentially, from the programming language, there were many submodels that were being trained at the same time. There was scheduling that took place across the cluster, pipeline of the output of one model training going to another across the board. And again, 6 weeks straight out to produce the model that then we could do inference on. So I'm not going to spend a lot of time on this. The press over the past few weeks has done a nice job of showing what you can do with large language models today. But here's one of the ones that I like. You can do things like explain jokes. And here's a joke. Did you see that Google just hired an eloquent whale for their TPU team? It showed them how to communicate between two different pods. And the model response, I'll read it to you. TPUs are a type of computer chip that Google uses for deep learning. A pod is a group of TPUs. A pod is also a group of whales. The joke is that the whale is able to communicate between two groups of whales, but the speaker is pretending that the whale is able to communicate between two groups of TPUs. So a pretty good explanation. And maybe one of the things that's surprising to me is if I were I get the joke. I'm at Google, I know about pods, et cetera. But if I were asked to explain the joke, I'm not sure that I would have come up with a better explanation than what this did in terms of explaining the joke. It's, and again, one large training model. You could imagine specializing it, but it can do a number of different things. It can turn word problems into code, right? And so here's some examples of some math problems. In this case, it's simple, but it can actually solve surprisingly hard ones with increasing accuracy. And maybe as interesting to me is it can actually describe the steps through code that are taken to translate the math word problem into a solution. So I feel like, again, we are at a place right now where we're starting to glimpse the future. Right? And we don't exactly know what the future is going to hold. But one of the things I think that we can essentially take as a given is that it's going to look very different. And the kinds of applications and the kinds of services that we're going to be running are going to be very different than what we've grown accustomed to over the past, let's say, 10, 15 years, right? Enabled by the last generation of breakthroughs. And I think it's fair to say, and we're seeing this, and I think the whole community is saying this, is computing infrastructure, networking, storage is going to be a limiter. Right? And we're going to need much more than we're able to deliver. How do we do that? And I think that, again, the techniques that we've used previously over the past 20 years no longer apply. We have to do things differently. And this shows it in stark terms. So this is the scaling of dense large language models from 2018 to, let's say, roughly about now, so 5, 6 years. And essentially what we're seeing is a 10x year over year. And this is public information. This is not Google only. This is what everybody's doing, essentially. And there's a good debate, hey, is bigger better unknown? And I think that at some point bigger won't be better. But however you wind up improving things, and there's lots of room for improving on the algorithm side, the main thing limiting our users is our ability to affordably build compute. And we're at a place right now as a community where maybe some of the big companies out there can afford to increase their spend on ML infra by another 10x. Let's say they are. They're not going to be able to do it by 100x. Right? And if we're at a place now where we're not able to wait for hardware to get faster to deliver the benefits, that means we have to do things differently. If we're going to, so again, the limiter here is how much we're willing to spend on compute. If we had spent more on compute, these large language models would be larger, or they would be doing things differently, et cetera, et cetera. So how do we continue to scale to meet their needs? OK, so that's vignette 1 and how judicious specialization and specialized hardware makes sense. Vignette 2 focuses on optical circuit switching. And here, the question is, how do you redesign for system-level efficiency? We talked about, so here I'm going to be focusing on the network in the building, in the data center. And we talked about this earlier on. But I want to paint a picture in terms of what kind of bandwidth you need at the scale of, in this example, I'm going to say there's 50,000 servers in a data center building. I'm going to simplify the problem quite a bit. Let's say that I've got these 50,000 servers. And let's further say that I've got 128 cores for each of these servers running at 2.5 gigahertz. Let's say that I connect them via a 200 gigabit per second NIC to the network. I might also have spread across the network some flash that can support 100,000, maybe a million IOPS. Maybe some flash that can have 100 microsecond latency for access. Maybe actually it's going to go down to 10 microsecond latency for access. If you do the rough math here, there's this old rule of thumb that's applied surprisingly well that says that for every megahertz of computation, you need a megabit per second of I/O. This is from the late 60s, Gene Amdahl. Amdahl's, some people refer to it as Amdahl's second law. But the point here is that this is a rule of thumb that tells you how to design your system for balance. You don't want to have too much compute and not enough I/O, right? Because if you do that, then your compute is starved waiting for data to arrive, right? Computing can't happen unless it has data to operate on. So Amdahl's second law gives you a rule of thumb that, again, shockingly over 50 years, has held up that says, here's roughly how you might provision, such that you're not overspending on I/O, but you're also not stranding your CPUs waiting for data to arrive. If you do this math, this says that your building with 50,000 servers would need a 10 petabit per second aggregate bandwidth network, or 10 petabits per second. So that's hard to put into context. That is something like 10x larger than the bisection of the entire internet. And now we're saying, OK, we want that in every building. And Google's got a lot of buildings, Amazon's got a lot of buildings, Microsoft's got a lot of buildings, Meta's got a lot of buildings, a lot of people got a lot of buildings. And we're going to put a lot of this into each of them. Now, maybe Amdahl's law was off. Maybe he was being generous and asking for too much I/O. But even if he were off by a factor of 10, you're still talking about putting an internet bisection in every building, a petabit per second, right? An enormous amount of bandwidth to keep the system balanced and to keep the system running efficiently. Excuse me. So going back with a bit of history, how did we support this? So we actually do this, and not just us, others do as well. Our initial approach to this, a system called Jupiter, that essentially goes back to some of the design patterns from the past, let's say, 20 years. It takes commodity silicon, and it organizes it in a hierarchy, closed topology, tree-based topology, where servers start at the bottom, and then they are in, let's say, a group that might correspond roughly to a row in that picture I showed you earlier of a data center building. They connect to an edge aggregation block that then connects in a tree to a spine layer, and all this is built out of the same building blocks. Furthermore, it's all under centralized control. So one of the things that, again, we've, as a community, pulled together over the past 20 years is a shift from internet-style, fully decentralized, peer-to-peer protocols to centralized control. So what you see on the left-hand side is a traditional network, where essentially, putting some of these numbers in perspective, for a 50,000 server data center building, you might have approximately 10,000 switches. It might be lower, might be slightly higher. But now how do these switches figure out how to send data to one another? The traditional way of doing so is they exchange messages pairwise. In other words, these switches are connected to other switches. They know their neighbors. They exchange some messages with one another. They learn the topology, and they learn how they forward data to one another. So everybody talks to their neighbors. Everybody learns the global system configuration. and they then figure out how to send data among themselves. That's a traditional decentralized model. We and others went after a different approach, which is to essentially take the computation out of each of these individual switches and put it under centralized control. So rather than have the switches exchange information with one another, they're directly connected peers, we had them exchange information with a logically centralized controller. Right? So you see this server up at the top left on the SDN side of the picture with 1000x compute power. The idea here is that you can turn pairwise communication among peers to centralized communication to a single controller that then actually knows what the blueprint for the entire system is, rather than everyone discovering and rediscovering what the topology is. And every time there's a failure or there's a shift, hey, let me recalculate everything from scratch. In SDN, what you say is, hey, you're the server, or you're the switch, excuse me. You have this ID. I actually know exactly where in the topology you're supposed to be. Oh, and by the way, I know exactly what your forwarding table needs to look like. And so let me just tell you the answer, rather than have you recalculate it. It turns out that this approach is actually fundamentally less expensive, but fundamentally faster and fundamentally more reliable, because you're now taking, without going into the details, what used to require n log n communication and turning it into order n communication. And n log n is best case. Many existing protocols in networking actually did worse than that, some of them even n factorial, as some folks I think in this room helped show. Okay, so fundamental shift in terms of focusing on the end system design and knowing what you're trying to achieve end to end. Now, this made it possible, actually leveraging commodity parts, to then build a 10,000 switch data center network that was essentially non-blocking, and getting you to that place where you could say, hey, I can have between a petabit per second and 10 petabits per second of non-blocking bandwidth within a data center building. For me, this was cool, but actually it's the now capabilities that you get that were particularly exciting. So some of you may be familiar with the CAP theorem. This is some work that Eric Brewer did. And essentially, what it says is that you can't have consistency, availability, and partition tolerance, C, A, and P, simultaneously in any distributed system. Okay? And you can pick two of these, any two of these, but you can't have all three. At Google, the spanner system that we built seems to violate the CAP theorem. At least for all intents and purposes, it seems to deliver consistency, availability, and partition tolerance for our distributed systems. And so Eric actually, he wrote this article. I didn't ask him to write this article, but I'm glad he did, where he says, actually, it doesn't, but the reason that it's able to work is because you can now drive huge amounts of bandwidth cost effectively between Google data centers, such that for all practical purposes, you can't have a partition. And now you can have a partition. In other words, if you were an adversary, you could go to Google's network and you can create a partition, absolutely. But because we got to a place where our approach to building networking was from first principles so cheap that it was close to free, we could, compared to compute and storage costs, we could afford to deploy so much bandwidth that it became effectively impossible, certainly relative to the probability of other events taking place, to create a partition. And that gives this illusion from the developer's perspective that you can have a wide area consistent database that seems to violate the CAP theorem. Now, okay, so now you had the SDN, cheap bandwidth, you can have spanner, which from a developer productivity perspective has been really powerful. But the software-defined networking gave us further ability, and that was the ability to introduce technology that was thought to be impossible to deploy in the data center, and that is optical circuit switching. So let me describe what the idea here is. What you see in the right-hand side of the picture here is a chip, essentially, that has 160 or so, 128 to 160 tiny mirrors, each under the control of a tiny motor. So it's called a MEMS array. And essentially what we are able to do, what we went after, was the ability to build optical circuit switches where you could bring in, let's say, 128 fiber pairs to a switch with one of these chips at the heart of it, and essentially shine all the light corresponding to the petabit per second, 10 petabit per second of bandwidth that crosses the data center building, well, a subset of it, onto these chips, and control the mirrors, the motors controlling these mirrors, so precisely that you could reflect the right light back out the right output port. So now imagine having a 128 port N by N optical circuit switch where you can reconfigure the crossbar at approximately a millisecond granularity. So you could create arbitrary topologies under programmable control for all the approximately 10,000 ports that might cross the data center building. Now, you can solve actually what was for us an age-old problem at Google, in that once you, let's say, build a 100 gigabit per second data center building network, like the one that you might have on the left, you can't incrementally introduce a 200 gigabit per second network. It would take me a few minutes to describe why, but so I'll give you an unsatisfying answer. But essentially, every switch connects to every other switch. And you can't incrementally introduce 200 gigabits per second because most of the 200 gigabit links that you would introduce would downclock to 100 gigabits per second. So the only way that you could upgrade the building from 100 gig to 200 gig, or from 10 gig to 40 gig, or from 40 gig to 100 gig, would be to burn down the whole building. Not quite, but stop, like tell everyone get out, which users don't like. Tear down the network and put in a new network, which takes months and is inefficient and labor intensive. So what we could do with the circuit switch then is essentially replace the spine layer where we had the all-to-all connectivity with these optical circuit switches. And we could reconfigure the network such that you could incrementally introduce, let's say, 200 gigabit per second, one at a time. And again, I could explain it to you, but I'll run out of time. We could then create the crossbar in a programmable manner such that all the 200 gig links connect to other 200 gig ports. And you could incrementally move as you need, sort of one block at a time across the building to the new network technology. Furthermore, what you can do is you can actually program for locality in your communication patterns. Let's say you're running a big machine learning job and you know that you're running it between two rows, two what we call super blocks. You can now program your optical circuit switch to concentrate more bandwidth between those two super blocks. Previous technology essentially said it had to be all-to-all. It had to be uniform. It had to be exactly the same everywhere. And with these optical circuit switches, we can now dynamically reconfigure the topology in a programmable manner. So judicious specialization plus application co-design in Jupyter. We did specialize to commodity silicon. We moved to software-defined networking for 10x improvements in reliability. As importantly, I didn't describe this, we moved to software speeds for feature velocity. So in other words, we could leverage all of our existing software development methodologies to roll out new features to that centralized controller. If we wanted to do a new routing protocol, A, the new routing protocol was much easier because it was centralized. But B, we could test it and distribute it very, very quickly. Didn't talk about this, but we also designed data center specialized transceivers. Previously, the things that would convert from electrical to optical and back to electrical as we went from switch to optics to switch were very expensive and specialized for the wide area. We designed them for the data center network. We moved to optical circuit switching to allow us to evolve the topology, but actually now you can think of it as the optical circuit switch as being the backbone for the building. And you now plug in multiple generations of hardware. So the beautiful thing about optical circuit switching is it doesn't care what rate you encode data at. It's just reflecting light. So as you move from 10 gig to 40 gig to 100 gig to 200 gig to 400 gig, the optical circuit switching doesn't get upgraded. It's still reflecting that same light from port to port, just like it did before. You can do application-specific placement and scheduling. And again, didn't have time to talk about it, but you can also go all the way to the end host to look at how you do congestion control. So taken together, what we were able to do here is, again, deliver not quite the same levels of improvements, but 10 to 100x system efficiency plus scale that essentially made the network invisible. So let's see. For time, as I predicted in Word, I won't have the ability to tell you about the software-defined servers or the third vignette. I do want to highlight one aspect of this for you all that I find important. As we specialize, one of my big fears is with TPUs and with GPUs, we've had it a little bit easy in that actually we were offloading a huge amount of computation from the CPU in a big batch to the, let's say, GPU or TPU. That makes it easier to offload. I worry that the next generation of accelerators that we must build aren't going to have the same benefit. And we don't actually know how to manage the level of asynchrony needed to deal with the fact that the coupling between the CPU, general purpose compute, and the accelerator is relatively loose, and the distance between them is large. So if you try to take general purpose code written in the standard von Neumann model and say, okay, I have this beautiful sequential code that's easy to write and easy to reason about, and I want to offload a portion of it, unless that can complete really, really quickly, and by really, really quickly for me, I mean an L2 cache miss time, like 20 nanoseconds or something, you're going to have to change your programming model. So if we're going to drive new offloads, we have to think hard about what the programming model is. And I worry because we haven't really conquered multi-threading from an ease of use perspective, and this is going to introduce one more level of complexity. Okay, so let's see. I will wrap up and leave time for hopefully a few questions. What I want to make sure I leave you with is that we have new requirements around societal infrastructure, security, sustainability, and sovereignty that really actually say we are going to need to maybe accelerate the amount of computing that we deliver to the community. That's on the demand side. On the supply side, the techniques we've used to scale no longer apply. So we have this incredible need for scaling out, but actually we're lacking the design patterns. So and I find this exciting. I mean, on the one hand, it's scary, but I think that the absolute critical need to do things differently and solve these problems and the opportunities that are going to unlock are immense. So how do we, and I know we will, we always have, how do we as a community rise up to meet this challenge? I'll leave with some, hopefully take some questions if there's time, but I'll leave this slide up in terms of a number of different ways that I think and hope we can collaborate, certainly between industry and academia. Okay.
Thank you. Thanks, Amin. I'll start with a question. You're talking about making a revolutionary change as opposed to an evolutionary change. And I'm just wondering how we get there without, as you say, burning down the data centers and starting over.
Yeah, it's a great question, and I think that's a number. One of the things I worry about is the innovator's dilemma. Like, we have a huge amount of code and infrastructure built in a particular way and growing really rapidly. I think it's going to take judiciously picking the right problem sets and being faced with a scenario where actually our existing solutions can't possibly work. I mean, that's what I love about the TPU example is, wouldn't it have been way easier? Like if we had just said, hey, we need to spend 50% more money for this use case to support inference, right, real-time voice recognition, we probably would have said, yeah, let's do that rather than build new hardware. I think that the path forward here is that there's going to be these application opportunities where we just literally cannot, and this is where the necessity part comes in. We literally cannot just say, I'm going to take an imperfect solution and apply it because I can't. So I don't know if it's going to be burning down data centers, but hey, wouldn't it be cool where we can do things like, say, the equivalent of liquid cooling for TPUs? We're going to build new data centers, and we're going to do them completely differently, and we're going to put new hardware in them, and they're only going to be for a subset of use cases. But again, just 7 short years ago, could we have predicted that TPUs are going to be some substantial fraction of Google's footprint? No, but they are, right? And you start with that first step. So, yeah. Louise or
I'll use because we're going to talk more later. So so when you talk about how demand for compute is growing at 10x per year, and I think about the other side of that equation where we can't make power grow by 10x per year.
Exactly.
And we're at the bottom of what we can squeeze out of transistors even at 2x per year, or 2x per 2 years. The only thing left there is efficiencies. And you can make your gas lamp become an incandescent bulb, become a fluorescent, become an LED, but then there's an end of the line there too. Do you, like, it seems like it's hard not to forecast that demand can go up all at once, but we're going to run out of supply.
Exactly so. So we are going to run out of supply, and as I said, we can imagine, could we imagine delivering another 10x for fixed power and cost? Maybe we could imagine it. We could argue whether we should or not, but we can imagine it. Could we deliver another 100x? I don't think so. So now the question is, okay, is there a new architecture that you would need? Just as TPUs were, and GPUs, by the way. It's a Google-centric presentation, so take it for what it's worth, but there's a lot of other great work and a lot of other great hardware out there. So one answer is, do we need, let's say it's driven by large language models. Is it the case that actually there's some other specialization of hardware that is 10x more efficient than TPUs? Are there algorithms that are 10x more efficient? Absolutely. Are we leaving 2x and 4x in utilization on the table in our infrastructure? And we do a pretty good job, actually, at Google, and I'm sure others do as well. So there are these other systems level things that you can go after to get you that next 10x. I think that there's actually a bunch of opportunity there. And you're right that it's not just going to be, we'll just build bigger TPUs. That's not going to get us there.
I guess another variant of the question is, how many years can we supply 10x improvements at the application level?
10x, yeah, great question. I'm not optimistic of us being able to do 10x for many more years. And I think that in terms of compute needed, we're going to have to figure out how we get more efficient with our algorithms, more efficient with our utilization, and more efficient with our hardware. I do think that what I do also know, on the other hand, is that we can't just simply say we'll live with 3 and 4% year over year.
So what are your thoughts on managing systems design complexity here? Because all of these avenues forward here, we're talking about increasing hardware diversity, network complexity, probably even more reliability issues that have to go and deal with. So one could argue that, hey, you could break down abstractions to say even to increase the efficiency even more, but then that makes it even more complex. So are you implicitly assuming here that you're going to use everything you learn about machine learning for systems design to manage that, or in more of a principled way of?
Well, so remember, I got my PhD in operating systems. And operating systems, people like to come up with convenient abstractions on top of complex hardware. Right? So I think that there's actually going to be, and we were talking with the grad students here over lunch about this, I think that there's going to have to be new abstractions that hides and manages this complexity. And again, I don't know what those are, so I don't have the answer for you. But I think it's fairly clear that our systems are going to be much more complex at the base level. And I don't think it's avoidable, honestly. In other words, putting it this way, I personally resisted having more than one server that we run on at a time, because it didn't make sense to until recently.
I was thinking about the opposite, actually, not having abstractions at all and just say, like, hey, humans are never going to program this thing anyways. It's all going to be designed by your large models. I'm actually somewhat serious here that should we really be thinking about elegant, human-readable abstractions, or just forget that? And
if I'm looking 3 to 5 years out, I don't see a path where we're going to not be able to have the humans drive it. Now, you're right, though. That's an awesome research direction, and we should be aiming for that. And I do think that on the system side, there's massive opportunities for ML to help with the complexity.
I had a question. I saw on one of the first slides we talked about the demand for carbon-free computing.
That's right.
Maybe I wasn't paying close enough attention, but I didn't hear anything about technology going in that direction from the slides. Can you tell me more about what needs to happen or what's going on there?
Yeah, it's a whole separate topic. So at Google, we have a goal that by 2030, all of our data centers are going to be running carbon-free 24/7. Right? Right now we're in a place where it's carbon neutral, but we achieve that by getting offsets in certain places at certain times. So it's a massive focus for us overall. But I think that, as someone was pointing out earlier, there's only so much power that you can generate. So making it carbon-free is a absolute fantastic goal, and one that we and others, it's not just Google, are committed to. But I think the interesting related question, though, is actually the embodied carbon emissions that comes from building the infrastructure, delivering the infrastructure, et cetera. And I think that as a community, separate talk, and I'm probably not the best person to discuss it, but we as a community probably need to focus more on that side of it. I think that 2030 plus or minus, we can get to carbon-free for our power consumption, but that's once the stuff is in place and running. Tool?
I'm kind of curious about the fourth S there, sovereignty, and what you're seeing and how things might kind of shape up. There was some thesis that might, this large infrastructure itself may not exist because, Germany or China does not want to do business with, Google or something. And like this idea of building like massive global scale, centrally controlled systems, like, do they kind of run into headwinds? Like, do you need 100 different control planes entirely because of local requirements, not just because of law? Like, where's that going to?
Yeah, great question. So I think the question here is, again, I did talk about the secular sea change where we went from decentralized control to centralized control. I do see that secular sea change now heading in the other direction, where one could imagine saying, I want to make sure I have infrastructure that independent of what, I won't name a particular company, but large global tech company, whatever they do in the US doesn't impact what's happening in Germany. And you're right that there's architectural implications up and down in terms of how you would design the control planes in such a world. Is there, yep.
So Google might be able to do this, Amazon might be able to do this. What about smaller companies? What chance do they have to be able to, if they need this kind of compute, is they're going to be like AWS for everybody else, or are they just not going to be able to build this infrastructure?
Yeah, I think so. One of the big benefits that smaller companies are going to have is the lack of innovator's dilemma. So let me give an example. Let's say that I've got a brilliant new insight where I can make some workload 10x more efficient, right? 10x cheaper, 10x whatever, but it's only 10% of my workload at Google. I may rationally decide that I'm not going to invest in that. That's what the innovator's dilemma essentially says, is that for that 10%, I'm just going to eat the cost and let that be way more expensive than it needs to be. Now 10x is a lot, but what if I said 5x? What if I said 2x? At 2x, I'm probably going to say, oh, that's not worth it. A smaller company, hey, if I've got an idea for making 10% of Google's workloads 2x more efficient, that's a pretty big opportunity because they get to laser focus on that 10% of the workloads. So I actually think that academia, smaller companies, when there's a revolution happening, I think that actually there's a massive opportunity, much more, let's say, broad opportunity across the community. So I think that smaller companies, I think academia are going to be playing leading roles in defining this next generation of computing.
Thanks, everyone, both here virtually and physically. Thanks very much, Amin. That was really great. Bye-bye.
A lot of fun. Thank you all.